Okay, so in this last part, we're going to combine some of the techniques, the two techniques we learned in dealing with non-homogeneous problems. So once again, let's analyze the problem at hand and anticipate some of the challenges and plan essentially how to solve the problem. This problem will not be done completely with all the details, so you should fill in the details for any part when I'm going to say, you know, suppose this is done, or assuming this is solved, then we get this. Simply because it will take too much time to deal with, write every single detail. And in some examples, it's useful to focus on the main points and leave the details to you as an exercise. It's very easy in these problems that are too long to lose the track of the main idea. And you should expect that many of the boundary value problems you will encounter in life, so to speak, will be able to be solved by a combination of techniques. So it's essentially splitting the large problem into subparts and keeping track of what you did, so you can get back to the original solution once you complete every single step. So this is a heat equation, right? So the rod is of length pi. It's non-homogeneous, but notice, unlike the previous examples, we also have non-homogeneous boundary conditions. And the method of variation of parameters, remember, required boundary conditions which are homogeneous. We also have some internally generated heat, which means we have a non-homogeneous term that depends on T only. So this tells me that I'll have to try variation of parameters, but that will work only with non-homogeneous conditions. Excuse me, with homogeneous boundary conditions. So I can essentially end up with a Sturm-Liouville problem, right? That's the key thing, you know, I mean, to figure out the Sturm-Liouville problem corresponding to the homogeneous part of the equation, but you know, you also need homogeneous boundary conditions. So remember that before we studied the method of variation of parameters, we dealt with non-homogeneous problems by making a substitution, by replacing the dependent variable, small u, with another one, big U of xt, plus some function of x only. You could try to do this substitution by passing the non-homogeneous conditions to h of x. So if you can determine h of x such that the new problem in big U is homogeneous, then you're good to go. Now, I know already this method will not work for the full problem, because again, this will only work if your non-homogeneous conditions are either constant or depend on x only. So for example, if here this non-homogeneous term depending on x only, you could have tried this and see if you could actually solve the whole problem just with this substitution. We know already we cannot do that, but we can still use this substitution to obtain homogeneous boundary conditions. So that means the goal is to essentially change these conditions into big U of 0t, big U of pi t equals 0. So the new problem in big U won't be homogeneous because this e to the t, this pesky term here, is still there, but you will have homogeneous boundary conditions. And from that point on, we could use variation of parameters for big U. All right, so let's do this part first and obtain the equivalent problem in big U, hopefully with homogeneous boundary conditions. So this part you should remember because it's familiar from what we covered before the exam too. So when I replace, when we substitute big U, excuse me, when you substitute little u of xt with big U of xt plus h of x into the PDE, we're gonna get big U t on the left. Yeah, partial t gets rid of h of x. and a squared partial little u partial x twice becomes big U partial x twice plus h double prime of x plus e to the t. Boundary conditions become big U of 0t plus h of 0. This should be 2. Big U of pi t plus h of pi. This should be 5. And because we want the new problem in big U to be homogeneous, this means h of 0 should be 2, h of pi should be 5. Don't forget the initial condition. Plug in the substitution there as well. Big U of x0 plus h of x should be x plus 2. So in the equivalent problem in big U, the initial condition big U of x0 will be x plus 2 minus h of x. And finally, the new problem in big U should be as simple as possible, basically. I mean, homogeneous in terms of boundary conditions. There's nothing I can do with this one, but we can certainly make the condition h double prime to be 0 so that we end up with a clean boundary value problem. Homogeneous in boundary conditions with the only non-homogeneous term being e to the t. So h double prime of x 0. That's the last condition on h double prime of x on h double prime. So with these conditions imposed on h of x, you obtain the problem that's hopefully determine h prime h of x. So h double prime is 0 with h of 0 equals 2, h of pi equals 5. We have met this before. So remember, if I integrate twice h double prime of x, that means h of x should be just a linear function in x. Now impose its conditions. H of 0 equals 2. That gives me n equals 2. And finally, h of pi, m times pi plus n, which is 2, equals 5. That gives me m equals 3 over pi. Okay, so with that being said, h of x is equal to 3 over pi times x plus 2. And of course, now the initial condition for the problem in big U will be x plus 2 minus h of x, minus quantity 3 over pi x plus 2. 2 cancels. We can pull out x, and that gives me 1 minus 3 over pi times x. So I know that for some of you, this seems like a lot, but again, we just basically finished the first battle in conquering this problem, so to speak. All we did so far, we changed the problem from the original problem with non-homogeneous boundary conditions to another non-homogeneous problem, but with boundary conditions now being homogeneous. So let's actually write it down on a different piece of paper. So the problem in U, in big U now is big U partial t equals a squared, big U partial x twice plus e to the t, with big U of 0t equals big U of pi t equals 0. That was the goal. And big U of x0, 1 minus 3 over pi times x. And don't forget that, in fact, my original solution, my original dependent variable is big U of xt plus h of x, which again we determined to be 3 over pi x plus 2. So when I'm done with solving big U, I'll have to add h of x, and then that's the solution to the original problem. All right, so now how do we deal with the big problem in U? Okay, it's not homogeneous, but it is perfectly suitable for the method of variation of parameters. Because we have Dirichlet condition on the interval 0 pi, we can go a little bit faster now. We could say, okay, I know that for the homogeneous part of this problem, if I were to solve it, I'm going to end up with the eigenfunctions in the form of sine of nx. Eigenvalues n squared, eigenfunction sine of nx. So at this point, we're going to look for a solution of this problem in the form of a series with coefficients depending on t yet to be determined. Okay, what else? Well, what else is that we're going to need a Fourier sine series on the same interval for u of x0 for this function, and for the coefficient of e to the t, which is 1. So now I'm going to look at the table and get 1 as a Fourier sine series in the interval 0 pi, and that is going to be summation from 1 to infinity. If you look at the table, 2 times 1 minus 1 to the n over n pi sine of nx. Then we also need a Fourier sine series for 1 minus 3 over pi x. Well, all we need is a series for x and just multiply the whole thing by 1 minus 3 over pi. So again, from the table, this will be, let's see, 1 minus 3 over pi summation from 1 to infinity, 2 minus 1 to the n plus 1 over n sine of nx. And then we're going to proceed with the variation of parameters, right? We're going to plug in this into the problem. You know the drill already. So let's do it. Partial t on the left, summation an prime sine of nx equals a squared partial x twice. Let's differentiate inside the summation. Let's see, if I differentiate sine once, that's n cosine. Do it one more time, that's minus n squared sine. Then plus 1 times e to the t, but instead of 1, plug in the series. So e to the t summation from 1 to infinity. Write that down. And then plug in the series, plug in, of course, the summation, you know, this format for u of xt into the initial condition together with the series corresponding to the right-hand side. Okay, so u of x0 is going to be summation from 1 to infinity an of 0 sine of nx, and that's equal to 1 minus 3 over pi summation of 2 minus 1 to the n plus 1 over n sine of nx. So I'm going to extract the problem in an, the equation that gives you n of t, and I'll leave it at that. And then feel free to solve it. with the formula that we discussed later on, the I1 and I2 formula. All right, so what is the equation that gives you n of t? Well, an prime equals, let's see, the coefficient of sine, right? It's minus na squared an. And here the overall coefficient of sine is 1 minus 1 to the n over n pi e to the t. And the initial condition for this problem comes from the initial condition of the PDE, which is 1 minus 3 over pi 2 minus 1 to the n plus 1 over n. So I'm going to pause for a moment, and I urge you to continue and determine an of t. That's the last part of the problem, basically. Not forgetting, of course, once you determine big U of xt, all you got to do is to add again h of x to provide a solution to the original problem. So I want to comment a little bit before we call it a day, because again, I am very aware of how complicated all this may feel, how tedious these problems may feel. And again, to actually make it easier, well, first of all, again, make sure you understand very well the theoretical background behind it. So, I mean, never write anything down without understanding the purpose of what you write down, because mechanical memorization of techniques, like trying to imitate, essentially solve problems by changing numbers without really understanding the logic of it, will never work in courses like this. It should be avoided at all costs in any courses, but in the courses like this, it will never work, and you only build frustration basically along the way if you don't actually force yourself to understand. Once you do that, it should feel actually easier on a conceptual basis. I'm not saying it's easy in terms of how much you have to write. It's quite tedious, and trust me, I mean, even myself, I'm getting bored at some point with so many series and summations. But on the conceptual level, it shouldn't be actually that difficult, because remember, all we do here in the end, we just basically take a format for the solution, we plug it in, and we just match the coefficients. It's something you guys did anyway in a different context in many other situations, right? I mean, method of undetermined coefficients, many partial fraction decomposition, many examples in which you match the left and right by simply matching the coefficients, right? I mean, whatever is multiplied by sine on the left is equal to whatever is multiplied by sine on the right. Now, of course, in this case, this results not in a simple algebra equation, but in another differential equation to be solved, right? Like a first order ODE. But again, for that, we have a formula. With this coefficient so ugly, again, it may seem hard, but these are constants. I mean, no matter how ugly, look at this, no matter how ugly is this coefficient of e to the t, it's still a constant nonetheless. So if we handle well basic calculus, we shouldn't be afraid of constants, right? I mean, no matter how widespread they look like, you know, or how tedious they look like. We'll just have to basically be patient and write it down. Same thing here. You know, we're going to plug in 0 for t to find some constant of integration. And then you just have to basically plug in this huge constant. It's still a constant. So this is the advantage of actually trying to understand the concepts. Because otherwise, again, it will feel harder than it is necessary. It's not an easy class, but it shouldn't feel harder than necessary. So with that in mind, that's it for today. I'll see you next time.